Okay, welcome back. In the previous video, we did a study of optimizing the YF-22 for its design mission and made the choice to give up some of its ability to do post-stall maneuvering and very high agility maneuvers by getting rid of the aircraft's large aft-placed pitch control surface. And instead we're using elevons for pitch control now. We can still rotate for takeoff, we still have good takeoff and landing performance, but at this point this aircraft would not be as maneuverable as the standard YF-22. On the other hand, it's arguable that a stealthy supercruising airplane shouldn't really ever be doing post-stall maneuvering at low speed. Perhaps it would be true that the wise way to use a stealthy supercruising fighter is to never get within visual range of another enemy aircraft. They can't see you, you can see them, you take them out with your missiles and you never get into a knife fight. It's nice to have that super maneuverability that the F-22 has if you actually did have a close encounter with an adversary, but perhaps it costs us a lot to be able to do that. And we saw that we saved $5 million per airplane by getting rid of that large horizontal stabilizer and pitch control surface, and then optimizing the wing plan form without that device. Well, that kind of a study is actually a trade study, and it gives the customer information on their options in specifying requirements for the aircraft. And in this video we'll do another trade study. The particular trade study we want to do this time is we want to look at that combat turn. If you notice in our constraint diagram, the combat turn is keeping us from moving further to the right. And of course, as we understand the sizing equation, if we can move further to the right, we'll end up with a smaller, lighter, less expensive airplane. So what if we said instead of being able to maintain 4Gs at 30,000 feet, we could maintain 4Gs at 25,000 feet? Once again, in combat we may not ever want to even go that slow. We may want to stay fast and shoot our missiles and bug out before the enemy ever sees us. And so perhaps it would be okay to just be able to sustain that turn at 25,000 feet. If you watched when I did that, the turn constraint now dropped way down, and it's not even an issue. It's not one of the driving constraints anymore. We could probably bring the altitude up to perhaps 27,000 feet before it even starts constraining our design. But let's optimize the airplane a little bit with the 25,000 foot combat turn, and we'll see where we go with that. So we've got the constraint diagram tells us that when we relax that combat turn constraint, the wing is now too big and we can make our wing smaller. So let's try 650, and it even goes smaller, 600. Okay, we're up against the landing constraint, but we have 400 pounds of gas. We can go to 58.7 for the weight. That brings us back. We can play that game again with shortening the takeoff distance and allowing more takeoff abort distance. And maybe that was too much. Let's try 26. Okay, so we're and once again it shows us that the wing is too big, so let's try 550. Alright, well, right over there we have takeoff and landing constraints, but the rest of the constraints are not drivers for us. we can drop our weight again to 58.4, and maybe even less than that. Let's try, well, yeah, let's try 58.3. All right. So we could probably stop here and say, look, I saved another $1 million. Oh, as we look at the design over here, we made the wing smaller. The elevons are too big now. Let's try 60 for the elevon area. Let's go back to 50. Okay, and we have lots of CN beta now, so we can make our vertical tail smaller. Let's try 120, 110, 100. And the tails don't go to the end of the airplane anymore, so we can move them further back. And once again, they're too big, so let's try 95. And CN beta is pretty good. We can drop down to 57.8. Okay, 57.7. And we're not anywhere near any of our constraints. We're in a very comfortable position with a little bit of margin on all the constraints. And we're a little bit above where we would absolutely have to be on thrust. So I'd like to try an experiment at this point. I'd like to try going to a single engine. Now that's a big leap of faith. It's going to be ugly for a little while. But if we do that and re-optimize the airplane, I think we might find a very satisfying result. Nothing to complain about so far. We've saved another $3 million, something like that, $2 or $3 million over the cost of each individual airplane, just by relaxing that constraint from 30,000 feet to 25,000 feet. But let's see what we can do with a single engine airplane. So we set the number of engines to 1, and oh, it's terrible. We got all kinds of problems, yes, but we have a really fat fuselage that we don't need anymore. So for starters, let's slender down this fuselage. We don't have 2 engines anymore, so we don't need that big wide fuselage. Let's limit this fuselage to 7 feet wide. And when we get to 7 feet, let's just do 7 feet all the way down. Alright, that's a lot better. Now, we're not meeting any of the constraints, as you might expect. However, we're carrying 13,000 pounds of fuel we don't need, because we got rid of a 5,000 pound engine, and we got rid of a lot of, apparently about 8,000 pounds of fuselage weight. So let's go to 44,000 pounds and see if that doesn't help things quite a bit. Oh, let's go to 41,000 pounds. Alright, so we're back in business. We're meeting takeoff and landing constraints. We can probably see that our wing is way too big here. And so let's go to 450. Alright. And we may come back up a little bit on takeoff, because the takeoff constraint is more constraining now than the landing constraint. And again, our wing's too big. Let's try 400. Okay, we'll worry about takeoff and landing in a minute. we've got way too much vertical tail now, so let's try 85. Let's try 75. Okay, and the vertical tails are not on the fuselage anymore because they were 4 feet out. Let's move the vertical tails into 3 feet. Now they're on there, and we can move them back to 48 or so because they're smaller. And they can even be smaller. Let's go to 70. Alright, and the aircraft is starting to look really good. We've got 2,000 pounds more gas. Let's go to 39,000. Okay, for takeoff gross weight, that we may not be able to do 41,000 feet at 1.5 Mach just yet. So maybe we have to do something to help that. Maybe we need to do some area ruling or something. Well, let's look at the area ruling. We've got this saddle shape, which is not good. That means that we're underestimating the drag of the airplane anyway. And up here in front at 20 feet, perhaps we're too wide. Let's try settling in at 6 feet wide until we get back beyond that point. Okay. Right. So maybe this is 6.2 or something like that. Yeah, 6.5. Alright, and then we'll go 7 and maybe 7.5. What I'm looking at here is this saddle. I'm trying to make it go away. Well, maybe this is 8 there. Whoops. Maybe that's 8. Yeah, 7.7 or something like that. I'm just trying to smooth it all out. And there's 8. But then, when we get over here, this is probably 6.5 again. Drop that down, and oh, what that did for us. Because it makes AMAX smaller. Let's try 6. Yeah, see, and look how the curve now matches the ideal Sears hack body pretty well. And so this is a big benefit to us, saves us another 500 pounds of fuel burn, which we can then reduce the takeoff gross weight. So 38.5. Okay. We're getting close to meeting all our constraints. We're actually meeting that turn constraint, all the turn constraints. We have this acceleration constraint we still have to worry about. But things are getting better. The strakes aren't on the fuselage anymore, and so we should help that a little bit by moving them in. They're at 3.5 and they should be at 3. Okay, that looks better. And they could probably be a little bit smaller and still be, yeah. The inlets got smaller because they only have to serve, or 2 inlets serve just one engine instead of each inlet serving an engine. And so as a result, the strakes are actually part of the inlets, and they should get smaller as well. I'm going to move these inlets out just a little bit so they look a little better, like they're actually outside the fuselage so they could get some air in. And clearly we need to move the wing back. We're too unstable. So let's move the wing back a bit to 25. Okay. And there's a spike there. We should probably take the next one down to 6. Okay, good. And we could probably drop this one down to 7. Drop this one down to 6. I guess this is 7.5, maybe to smooth that out. 7.7 is still okay there, I guess. And then let's try 7.7 here. Yeah, okay. Dropped another 500 pounds, we can go to 38,000 pounds. Okay, and at this point we're almost making all of our constraints with one engine. Drop one more 100 pounds, it looks like 37,900. And the wing's too big. So let's try 370. Drop another 100 pounds. We're making our acceleration constraint 37.8. We are making both constraints. Our takeoff distance is 2941. We said 3,000. Our abort distance is 4841. We said 5,000. And our acceleration is looks like it's being met as well. We're crowded up against all the constraints, and so that's a concern. We'll drop the aspect ratio down to 7 for the elevons to make them fit on the wing better. Let's try 6. I don't want to make them any smaller because I need that pitch control. And once again, we can move the wings back, so we can move the inlets back. Let's move the inlets back 2 feet and then shorten them by 2 feet so that the engine stays where it was. And let's move the strakes back 2 feet. So there we are. We make our constraints. Perhaps we have really quite a bit of volume remaining, so let's try to recover the fuel we lost when we moved things around a little bit by narrowing the fuselage back here. Let's go to 6.5. Okay, and there's a peak here at 30 feet. So right now that 7.7 maybe should just be 7. Yeah, there we go. And we can drop this down. Let's go 737 maybe. And that's pretty good. Let's try 37,700. Alright. And again, we make our takeoff and landing constraints by about 100 feet. Let's quickly check to see if we make our 500 feet per second at 30,000 feet in Mach 1.15. Let's go to the piece of best diagram. Remember, don't look at that thing until you hit the calculate piece of best button. Okay, and let's look at, we're at Mach 1.15 and 30,000 feet. This is 600, that's 400, we want 500, so we're closer to the 400. So I believe we are making it. We're making the acceleration constraint, and we've got a pretty good airplane. Compare this airplane to an F-16. Oh, it's auto-saving. Wait just a second till it does that. There we go. Now we can take the F-16 and overlay it. This is a way more capable airplane than the F-16. It's got a lot more piece of S. This is, here's 0, 200, 400, 600, 800, 1,000 piece of S compared to the F-16's 800 piece of S. So it's still a very capable airplane. Not as impressive perhaps as the YF-22 was, but still a very, very capable fighter aircraft. And for another comparison, let's look on the maneuverability diagram. Now we have F-16 maneuverability at 10,000 feet. So to do a comparison, we have to change our maneuverability diagram to 10,000 feet. And now let's overlay these two and see how our airplane would compare with an F-16. Okay, so the F-16 can sustain just a little bit more. Here's the F-16, p sub s equals 0 curve. Here's ours. Okay, so at subsonic speeds, the F-16 can turn just a little bit better than our aircraft. On the other hand, at supersonic speeds, we can outturn the F-16. And so, for an aircraft that's supposed to be a super cruiser, that's supposed to go to the combat at supersonic speeds, I think you'd probably like this airplane compared to something like an F-16. In any case, we have given up 5,000 feet on our sustained turn, and in consequence, we have saved $40 million per airplane. That's pretty amazing. We could go farther. We have too much CN beta, so we could make the vertical tail smaller, like 62, and save even more money. And of course, before we give up on this, we should check and make sure we can still rotate for takeoff. Well, the CG moved a lot, and as a result, we probably need to work on the CG for a second. Notice that we have armament and everything else located well aft of the CG. The expendable payload, we should put that on the empty weight CG, because that's where we'd like it to be, centered on that. So let's go 33.4. Okay. And now, when we go to the gear tab, we see that the main gear are too far back. Let's try 35. Solve the problem. It's easy to rotate for takeoff still. We've got a decent tip back angle, right around 15 degrees. We're pretty good on 90-10 rule. We're on the 85-15 side of 90-10. We could massage this more, but really this is pretty good. We could maybe move the nose gear up to 20 and get closer to 90-10. And so we've got a very workable airplane that's $40 million cheaper than what we projected the original cost of the YF-22.